Here we have an abbreviated periodic table of the elements. These elements are going to be the ones that we're going to be using throughout Chem 343. The ones in green are not that useful to us. The ones in blue we'll see quite a bit of. Now, the periodic table is really divided into different families. If you number at the top, 1, 2, 3, 4, 5, 6, 7, 8. It's essentially the periodic table is divided into 8 groups. And these groups have very similar properties within a group. One group here is group 8, is the noble gases. These are boring. They do virtually nothing. They are very, very, very stable. They're stable because they have on their outermost shell 8 electrons. You can tell that because they are in group 8. And these numbers above each family tells you how many electrons are in their outermost shell. 8 electrons is a very stable thing. It's basically called the Octet Rule. Elements are constantly trying to get into this, have a complete octet around them, because that provides a deal of stability. Groups 1 and 2 here, these also want to have a complete octet, but they have 1 electron or 2 electrons in their outermost shell, not 8. And so what they do in order to get their outermost shell to be 8 is they have a tendency to give up electrons. Hydrogen is sort of an exception to this. We'll get to hydrogen after a bit. But the ones below hydrogen, lithium, sodium, potassium, rubidium, and cesium, these give up 1 electron. Beryllium, magnesium, calcium, strontium, and barium give up 2 electrons. And when they do so, they end up having complete octets. When lithium, that 0 means there's no charge. So this has a single electron in its outermost shell. When it gives up its electron to something, it becomes a positive charge. And this lithium is like helium. It now has the complete octet. Sodium, when it gives up 1 electron, it becomes like neon. Magnesium, when it gives up 2 electrons, it becomes like neon as well. Now, what do they give up electrons to? Well, they give up electrons to any of these other groups, particularly the ones in groups 6 and 7. Groups 1 and 2 give up electrons completely. They have a tendency to form ions, or charged compounds, positively charged in this case because they're giving up electrons. And they form ionic compounds. Say lithium gives up 1 electron. Well, fluorine is in group 7. That means fluorine has 7 electrons around it. 1, 2, 3, 4, 5, 6, 7. Each of those dots represents an electron. If it accepts an electron, it becomes F minus. This also has a complete octet. The compound lithium fluoride is an ionic compound. Where the lithium has given up its electron completely to the fluorine. And so another way of writing lithium fluoride is lithium plus F minus. Other examples of ionic compounds. Magnesium oxide. Magnesium can give up 2 electrons. Because it's in group 2. Oxygen is in group 6, so it has 6 electrons. If it accepts 2 more electrons, you get the O2 minus. So magnesium oxide is another ionic compound. You can draw it like MgO, or we can draw it simply Mg2 plus oxygen 2 minus. Other examples could be magnesium chloride. Here we need 2 chlorines because chlorine is in group 7. It accepts 1 electron each. Magnesium donates 2 electrons, so to balance that out, you need 2 chlorines. Okay. Hydrogen is somewhat special. Notice, hydrogen, if it loses its electron, it has no electrons. It doesn't have a complete octet at all. But if it gains an electron, it becomes like helium. And so, hydrogen's a little on the special side. Sodium hydride, NaH, a compound that we will use a lot in organic chemistry, is an ionic compound. We have sodium plus. Sodium gives its electron up to hydrogen, H minus. And so sodium hydride is thought of as Na plus H minus.